Hello, dear friends and students. Our video today concerns itself with polymers and polymerization. If you recall, we find that there are a number of uh, shorts and videos which have already been uh, published in YouTube by us. And the present video is also in continuation to the same subject. And if you recall, we have used a catalyst for preparing high density polythene HDP or low density polythene LDP. And there we have used a catalyst which was known as Ziegler-Natta catalyst. Our studies on polymers and polymerization cannot be said as complete until and unless we get an idea about what is Ziegler-Natta catalyst. It was called Ziegler and Giulio Natta, a German chemist and an Italian chemist. They discovered a catalyst which works well for synthesis of HDP, high density polythenes, and LDP, low density polythenes. In presence of this catalyst, usually termed as, in short, we can call it a ZN catalyst. Now we know that transition metals are well known for their catalytic activity. So to obtain ZN catalyst, transition metal halides belonging to group 4 to 8 are reacted with organometallic compounds that belong to group 1 to 3 in modern periodic table. So it has got Zn catalyst, a transition metal group 4 metal, and also an organoaluminum compound is a co-catalyst. Co-catalyst. When they are combined together, they are reacted together, they are synthesized together, we get Zn catalyst, Ziegler-Natta catalyst. Now, today we shall have an idea about Ziegler-Natta catalyst and how it is classified, what is the basis of its classification, and what is the structure of the common Ziegler-Natta catalyst using aluminum chloride as a co-catalyst, and also how it works. So without entering into mechanistic details or the kinetics of the reaction, we have to have an idea about what is Ziegler-Natta catalyst. Okay, so let us proceed. And as you find here, Ziegler-Natta catalyst is divided based upon its solubility into two types. As usual, it may be a heterogeneous catalyst or it may be a homogeneous catalyst. Heterogeneous catalysis is a supported catalyst commonly employed in the polymer industry. This is very common. Titanium compounds are used in combination of co-catalyst, and the compound is triethyl aluminum. Homogeneous catalyst is based upon the solubility. They are used in combination with different organometallic compounds. Methyl aluminooxane, we call it as MAO, is used as a co-catalyst in this case. Okay, then let us see what will be the formula of the Ziegler-Natta catalyst using titanium chloride TiCl4 with ethyl aluminum chloride. And the molecular structure, you can very easily write it down as AlCH3 twice, CH2 two times, Cl. And if you look at the structural formula is titanium chloride, titanium 22, TiCl4, and aluminum, ethyl aluminum, triethyl aluminum is here. So they combine together just by heating together under suitable temperature, you get a combination of coordination. We can say the titanium chloride gets coordinated with triethyl aluminum, and you get Ziegler-Natta catalyst like this. Now we have to see how it works. Okay, now we shall find out how Ziegler-Natta catalyst activates the system in a polymerization reaction. As we know, Ziegler-Natta catalyst is crystalline in nature. It is synthesized by the reaction of uh, triethyl aluminum with titanium tetrachloride and has a crystalline structure with coordination number 6,6, and therefore it is planar in structure also. And 5 chlorine atoms surround a titanium atom on the crystal surface. Still, an empty orbital is left over the surface which can be utilized or which can be filled up. Now, when it comes in contact or encounters the titanium chloride compound, it donates a ethyl group to the titanium atom. And simultaneously, one chlorine atom from titanium gets apart. So, the catalyst system reverts to its original structure, still possessing the vacant orbital. Now, how this happens is diagrammatically explained here in the other slide. As you find here, there is a central atom titanium containing 5 chlorine atoms, and there is a vacant orbital left over. Now, this again, when comes in contact with triethyl aluminum, as you find here, what happens that one chlorine atom is taken up by triethyl aluminum and it becomes Ale2Cl, but still there is a vacant orbital. So this continues in the system, and during the course of the reaction, of course, when it reacts with an alkene, a monomer of LDP or HDP, we get the similar reaction occurring, and a vacant orbital is available all the time for the interaction or for the reaction. Now, without getting into mechanistic principles or the kinetics of the reaction, we can very easily understand how triethyl aluminum works and during the course of polymerization. Okay, we stop here and we shall be back again after some time. Thank you very much.